Hello everyone, good afternoon. We're going to start with today's session. We welcome Douglas Hood. For Douglas, it's very early. It's great to have you here, Douglas. Thanks for joining us. And Douglas will take us in the SQL data caching, especially for performance. Patrick Barrel, my colleague, will be co-hosting this event. And he will take care of moderating the questions. So please, if you have a question, post them in the Q&A. And Patrick will pass them through to Douglas. And since Douglas likes to have interactive sessions, please be prepared that Patrick takes you into the session. So you can follow up yourself on questions if you feel it is relevant. Have a great presentation. And I'd like to hand over it now to Douglas. Succes, Douglas.
Dankjewel, Jelle. Goedemiddag. Ik ben Doug. Ik kom uit New Zealand. Ik spreek Nederlands. So if you're laughing, I don't speak Dutch.
Yes.
Okay, good afternoon, everyone. So my name's Doug, and I'm going to be talking about SQL data caching for performance and database offload. So I'm in San Francisco. I'm from New Zealand. I used to live in the Netherlands, in Amsterdam, many years ago. So we're going to be talking about caching. Caching is really easy to do badly. What I'm trying to show you is some of the pitfalls, some of the better ways of doing it, and how some of the largest systems in the world do it. So here are some of my customers, like TMobile, 946 million users, eBay, Apple. It's sort of a Fight Club situation. They don't really want to tell us what you're doing, but basically, if you've used Apple products, you've used SQL caching from Oracle. So last year at Open World, eBay did a presentation on how they are using SQL data caching. So eBay has virtually every database under the sun. They have all sorts of different caching technologies. And we went through a process of replacing some of those caching technologies, which were mainly SQL, NoSQL sharding, to using SQL because we could do it faster. So now 100% of the most common queries use Oracle application tier database cache. So when they first turned it on, they were doing about 1.4 million SQL queries per second. They're doing a lot more. So the point being, because eBay's large, they have lots of sharded databases. They needed to offload work. And just in the first week, they were able to offload 40 billion round trips. So when I say eBay's large, they have huge Oracle databases with many connections. Just a question. How many connections can an Oracle database have? What's the maximum number? Anybody? The maximum number of concurrent connections to an Oracle database. Okay, you might think it's 64,000. eBay is running about 84,000 per machine. And they shard that with lots of shards. So it's quite a big system. So also, so eBay is obviously a custom solution, their own data model, their own sharding infrastructure. A far more out-of-the-box solution is TMobile. They use Oracle Siebel custom relationship management for their customer information. And that works well, it's got a lot of functionality. But when you have 86 million users, it wasn't going fast enough for them. So we added application database cache for that to make it go faster. And last year at Open World, TMobile talked about how they did that. So the point is they had large rack databases running Siebel, and they used ×10 as a SQL cache in front of that. So this is actually T-Mobile's slide. So Siebel CRM was running on Oracle, and they had microservices to expose the relevant information for reads and writes. And the microservices, you know, they were all taking less than a second, but because a web page was calling many microservices, all those little bits add up. So this is a histogram. So the blue bar is the latency. When they added SQL caching, I'm not sure if you can see it, but that little green thing, it went a whole lot faster. So was it 5 times faster, 24 times faster, or 40 times faster? It depended on the individual microservice that they were running. So the point was, they didn't change SQL. They took their existing microservices, which was written in Java, and they just changed the connect string to talk to the cache, the SQL data cache, rather than the rack backend, and it went a whole lot faster. So they were happy. So that's sort of high level. It can make things go a lot faster. But let's now look at the theory of what you can and shouldn't do, and then how you can do it better. So whenever I talk about performance, not everyone's talking about the same thing. Performance is really about 3 things. Latency, which is how long one thing takes. Throughput, which is how long it takes for everything to happen at the same time. And scalability, which is increasing the throughput while keeping low latency. So fundamentally, why caching? And I deal with a lot of customers who do caching, and unfortunately not all of them understand why they're caching. And quite often they do it wrong, very expensively wrong. And we'll cover that. But at a really high level, you got some Oracle database. Is it single instance? Is it rack? Is it Exadata? Is it sharding? Doesn't really matter. You've got an Oracle database and you're connecting to it and you're doing some operation and it's taking some amount of time. Let's call it 1x, whatever that time is. The whole point of using some cache is it should take less time to access the cache than your Oracle database, your system of record, whatever it is. Because if it's not faster, what's the point of using a cache? So lower latency is the first thing you got to look at. Some caches aren't necessarily faster than going to the system of record, but maybe they're useful because they're offloading work from the system of record. If your applications are hitting some cache, it's going to offload CPU and disk I/O from the system of record. If your cache is significantly slower, I'm saying, what's the point? Now, this may seem really obvious, but I deal with some of the largest customers in the world, and these really basic things they don't understand or are getting wrong. So like, that blows my mind, but people are doing it. So one side effect of using a cache, if you have lower latency, as a side effect of that, you get more throughput because the reciprocal of latency is throughput when you have a single connection. When you have multiple connections, you can get more throughput. So that's a nice thing. If you have many caches, you can get significantly more throughput and lower latency and offload. So according to me, there's basically 3 ways of caching a relational database. It doesn't matter whether it's Oracle, MySQL, SQL Server, Postgres, pick your favorite technology. So you basically either log sniffing, using triggers, or polling. So there's different ways of doing that, but it all boils down to one of those 3 techniques. Log sniffing, various ways of doing it. I like using Oracle Gate because it not only allows me to get data from an Oracle database, but also a bunch of other databases. Triggers. So if you have committed inserts, updates, or deletes, the triggers fire. So there's pros and cons of log sniffing, and triggers will go into that. The third way is polling, basically doing a select against a table, how often. It kind of works, but I claim it's just dumb. Both log sniffing and triggers are event-based. You're getting data when things changed. With polling, you don't know when things are changed. So you're going, has it changed? Has it changed? So how often should you do that? So a lot of my customers use non-Oracle products. So they use all the cool open source, NoSQL, whatever databases. So they're using these technologies for caching because, a few years back, that was the cool thing that would solve all problems. But those customers who have all these technologies are coming back to me and saying, hey, we want to actually do it better. We wanted to have lower latency, higher throughput, and with less code. And we'll see what that is and why that is. So if you have a relational database with a data model with relations, if you have to somehow cache that in some NoSQL database, whether it's key value or some document store, you need to map from your relational data model into a different format. So what we're really doing there is ResultSet caching. So whether it's going to a key value or a document data store, it's really the same thing. You're taking some relationship which you're expressing as one or more queries and you're stuffing it into a different format. So it's fairly easy to do. You run a SQL query, one or more queries, to get the data. If you're doing joins, you're essentially creating a materialized view of that information. So you're sort of pre-computing it, and in theory it's fast because given a value, given a key, you can look up the value. So in theory it should be fast, but there's problems. The data you've cached is very dependent on the query that you created at that point in time. By definition, it's going to be stale. You probably have missing data. But probably the most evil thing is you need to completely rewrite your application. So instead of using SQL, you're using some other API and data type. So fundamentally, when you're using a system which is not SQL, you basically have to rewrite your application to use that caching technology. So there's another way of caching SQL data. If you use a SQL database to cache another SQL database, you've actually made things simple because you can have the same data model with the same data types, with the same relationships. So you can do a one-to-one mapping. So schemas, tables, columns, SQL statements can be the same. Obviously, it has to be faster. So let's just look at an example of a cache. So over 30 years ago, I wrote my first cache. I was using a mini computer. It was a VAX system. It was very slow. So whenever I did a query, it was taking over 10 seconds to show the information on the screen. So I'd done computer science. I knew SQL. I thought, let's write a cache. So I figured out, I was trying to be clever. I'd figure out how many records I needed. I then allocated an array of records to store them in memory. I then got a query from the database, and then I could do a linear search through my array to find the information and display it on the screen. So it worked, and I could update the screen sub-second, so it was pretty cool. I thought it was awesome, but there was some problems. Can you tell me some problems with this cache? This is where you guys get to pick apart this code. What is wrong with this code? Anybody? Are people muted, Patrick?
Everybody's muted, but they can say something in the chat. I see, how do you keep it in sync? Somebody says size of memory, things happening in time between.
Okay, those are all correct answers. So when you're caching things like this, I mean, this is really easy to do. You need to store that information in memory. So if you're caching 100 records, that's good. If you're caching billions of records, you need to have sufficient memory to actually allocate. If you don't have enough memory, that's not going to work. How do you know how much data? Also, I mean, I was doing a linear search. If you've got 100 records, who cares? If you've got millions or billions, it's going to take forever. But the biggest thing that was pointed out is, how do you keep what's in the database synced up with what's in the cache? I didn't. I did it once. So I had stale data. So the point was, it was easy to code. It was pretty fast, but it was fundamentally quite useless. So 30 years ago, I wrote a dumb cache. The really sad thing is, I work in Silicon Valley, and there's lots of companies who use really cool technologies, all the latest buzzwords, and they're doing the same dumb stuff. So it doesn't matter what language you use, what operating system, whatever. If you do dumb things, it's still dumb. So let's look at some of the fundamental issues with caching. Now, I believe these issues are independent of the technology. Whether this is an Oracle database, SQL Server, Postgres, whatever, these same issues apply. These are generic issues. So quantum entanglement, what's that about? This is not science fiction. This is real things which are slightly complicated. The point being, you can have subatomic particles where a change in one affects its buddy instantaneously over any distance. So it might be a meter away, or it might be light years away. A change in one thing instantly changes the other. Now, that would be perfect for a cache because both systems are always in lockstep and changes are instantaneous. That would be brilliant for a cache. So this does work in physics labs at the subatomic level. It doesn't work at the database level for rows, unfortunately. Maybe in the future, but not today. Something that is far more concrete is you can have replication. Is that 2 Oracle databases? Is it 2 MySQL? Is it 2 DB2? It doesn't really matter what the system is. You can replicate between them. The question is, should you do it synchronously or asynchronously? If you do it synchronously, both databases will be in lockstep. There'll be no difference between them, which, for a cache is great because your caches are going to be stale. But the obvious problem with that is synchronous replication is slow. It doesn't matter what the technology is. You got to, are you reading from triggers? Are you reading from logs? Are you polling? Doesn't really matter what. You got to capture the information. You got to transfer it. You got to apply it. And you got to do that really quickly. And the further apart they are, the longer than that takes. So the net effect is nobody uses synchronous replication for caching because it's just too slow. If you do it asynchronously, it's going to be far faster, but there's downsides of that. If you do anything asynchronously, by definition, the data in the cache is always going to be stale. So it doesn't matter what language you use, what methodology, how cool you make it sound, it's going to be stale data. Is it a millisecond stale? Is it 5 seconds stale? It doesn't matter. It's going to be stale. So just admit that up front. Also, some of you mentioned missing data. Is that a little bit of a problem, or is that a huge problem? If you're doing stuff asynchronously, something may have been committed on the system of record, but it's not yet in the cache. You haven't seen that. So it's going to be application specific how much that matters. Finally, there's no such thing, as a free lunch. There's an overhead of caching. You somehow have to capture those changes. Is it polling? Is it triggers? Is it sniffing event logs? You got to transfer it over a network. You got to apply it, and you got to keep it consistent. So all of that is an overhead. So it's tax. Nobody likes tax. Finally, do you need to translate? If you have your data in a SQL database and you're caching it in something that's not SQL, you got to translate the data types and the meaning of the queries at runtime. So that's a runtime overhead. And also as a developer, you need to change your SQL application to be some other API. So that translation is both a runtime overhead and a development overhead. So here's a question. If you have a system of record and you have a cache, I've just pointed out, because you're doing the refresh of the cache somehow asynchronously, this cache is always going to be slightly stale. But you don't want stale data. So here's a question. If you always check if the data in the cache is the latest, is that a genius design or not? So are we getting any responses on the chat, Patrick? Is this genius or is this dumb?
There's nobody answering yet.
Okay, I'll let them think a bit longer.
Dumb, and not. It's probably a dumb thing to do.
I think it's really dumb. So let's look at it. If your cache is really fast, I'm making up this number, say it's 10 times faster, so it's got a 10th of the latency. So how long these things take doesn't really matter. If you have to go to the cache to look at a value and then check if it's the latest, by definition, you're doing twice the work. By definition, it's always going to be slower. I think this is a ridiculous design. I go to the largest companies in Silicon Valley and they're flat out building these technologies because they think it's really clever. So maybe they know something I don't. I think it's ridiculous. So what I've been talking about is read caching. Your database over here is the system of record. So your committed inserts, updates, and deletes occur in your system of record. In the cache, you've just got some stale values. Are they a millisecond old? Are they 5 seconds old? Are they a day old? So you're doing read caching. Read caching is, in my opinion, fairly easy to do. Write caching, in my opinion, is harder. And here's why. We've got a database and we've got some backup system. Doesn't matter what the technology for the backup system is. Your database has committed inserts, updates, and deletes, and you do backups. Do you do backups every hour, every day, every week? That's up to you. Question, which is the system of record? Is it this guy or is it this guy? So is the system of record on the left or on the right? What sort of answers are we getting, Patrick?
I think people are still typing. Right. Both?
So some people think...
I'd say left. Left?
Okay, so think about it. I got my database and it caught on fire, it's gone, it's never coming back. My backup, is it an hour old, a day old, or a week old? It depends. So this is kind of an open question. I believe this is the system of record. Some people don't have backups or backups that don't work. I believe that this is a system of record. You may not agree with me, but just go with it. Let's look at another example. If you're doing replication, think DataGuard, think Golden Gate for Oracle databases, or if you're using some other technology, you're using some form of replication. If you committed inserts, updates, and deletes are here, and they get replicated to the other system. So if they're in the same data center, that may be fast. If you're replicating to the other side of the world, just the round trip time, it's going to take time. If the rate at which you can write to this guy is significantly larger than the rate at which you can replicate, so say we're writing at 10x, whatever x is, and we're replicating at 1x, that means that this guy is going to be behind, and over time it's going to get further and further behind. So the question is this guy the system of record, or is this guy? What answers are you getting, Patrick?
I'm waiting for the new answers. Confused, the right one. And it's probably right as in left and right. Left, left, left.
Okay, so we think the left one is the system of record. I agree with that. Okay, here's the tricky bit. When you have a write cache, the cache will have the most recent data. If you asynchronously write to your database over here, this guy's going to be behind. If the rate at which you can write to the cache is significantly faster than the rate that you can replicate, this guy is going to get further and further behind. So here's the question. Which is the system of record? Is it this guy, the cache, or is it this guy, the relational database? What answers are you getting, Patrick?
Waiting. Cache, cache.
That is correct.
The cache. Both, it depends. Left.
It depends. That's
No,
the good answer.
that's the Oracle answer. It depends. No idea, seriously. Both, left.
Okay, so the point is, if your brain is exploding, that is the correct answer. Technically, the thing with the most recent data is the system of record. But you don't want the cache to be the system of record. You want this guy to be the system of record. So that's kind of a contradiction. And that's the point. Unless all writes go through the right cache, this won't work. If you do some writes here and some writes directly to this database, you're going to have data inconsistencies. And in my world, that's bad. So I believe write caching is far harder than read caching because of this fundamental issue. If all writes go through the right cache, it can be fine. And I have a bunch of customers that do that. They design or constrain their systems such that all writes go through the right caches. If you have something like Siebel CRM, there's no way in hell that you're going to change Siebel to go through a right cache. It's going to do stuff its own way. Therefore, the only safe thing to do is don't do it. If you have control over the environment and you can force all writes to go through the right cache, you can be 10x, 100x faster than Oracle, RAC, or Exadata. It's awesome. But if you can't guarantee that all writes go through the right cache, just don't do it.
Doug, I think we have somebody that has a question. Raised his hand.
Do.
I'll unmute the person. Frans, you can unmute yourself. Or maybe not.
So I'm happy for questions. Like this is fundamental. It doesn't matter what technology you use, what language, pick your favorite buzzwords. These are fundamental issues. If you understand them, you can make good choices. If you don't, you can make an expensive mess. And a lot of my customers have expensive messes, and we go in, we point out the obvious, and we apply different technologies so they go from a mess to data consistency with lower latency and higher throughput. One's undesirable, the other's desirable.
Doug, I have a question coming up here.
Yep.
Can you have many simultaneous write caches?
Yes. But once again, I'm pointing out the issue with one. So is that write cache for one table or lots of tables? I'm saying it doesn't matter. It's the same problem. If you have, that write cache is running on a machine. Is it bare metal? Is it VM? Is it a container? It doesn't matter. You can have it running on one thing or many things. The point is the data consistency is still the same. And when we get further in the slides, we've got more pictures and examples of that. So just bear with me. So this is the most important slide in the entire talk. Which is the best sports car? There's some Italian car. I think that's another Italian one. I think that's a German one. I think that's a Dutch one. Which is the best car? I'm sure there's opinions.
It depends. It's the first one. The Dutch one.
The Dutch one. Okay.
We must know what is your goals. Porsche 911. Personal preference. For me, the Dutch.
Okay, those are all good answers. The most important question is, does anybody own one of these cars?
No.
Okay.
No, not yet.
We all wish.
So in the model, scale 6 to 500.
Okay. So the point is, everyone has their own preference. If you owned one of these cars, I believe you would say it is the best car because you're biased. If you were really rich and owned all of these cars, I would care what you say because you could objectively compare these things. So instead of, I like the color, or, my dad liked that model, so I like that model, just subjective things. If you've driven them all, then you can have feedback based on experience. Kind of makes sense? My point is, I'm not talking about cars. I'm talking about databases. If you've used them all, you'll know that they're all good at different things. They all have their own sweet spot. Some things are good at, some of these technologies, Mongo's got a document, Cassandra's key value. They have different things that they're good at, different strengths, different weaknesses. So my point is, my largest customers tend to have many, if not all of these technologies. Like eBay has all of these technologies. They have them in production and they have huge clusters of them. So they know what they're good at and what they're not good at. Okay, so because they have empirical experience, I care what they say. If you've never used any of these technologies, I don't care what you say. If you've only used one of them, I also don't care what you say because you don't have a reference point. You tend to be biased. I care about my customers that use all of them so they can give objective feedback rather than subjective feedback. So the point is, my customers have these technologies which they use for caching, and they tell me what they don't like about these technologies. So I've got this table about cache properties, I basically wrote down what my customers said about these technologies. Most of them found that it was actually slower to get the data from the cache than from the system of record. Slower. So they're using these they're using clusters of these technologies for caching. But when they have large clusters and millions of users, they're finding in practice it's slower to get the data from the cache than the system of record. Kind of crazy, huh? They also don't necessarily know how stale the data is. They're quite often missing data. There tends to be a high overhead of keeping the cache up to date, or as up to date as they can. So they're, are they firing lots of triggers, or are they mining logs, or are they polling? In practice for these large systems, the overhead tends to be high. All of the solutions aren't using SQL, so they're using some NoSQL API and they're all different. So my customers had to completely rewrite to use these technologies. So these are the things that my customers complain about. So if we look at the opposite, if you had a cache that was lower latency than the system of record, if you know how stale the data is, if you can enforce cache consistency and have lower overhead and minimize the data translation, preferably have none, and instead of completely rewriting your application, if you just change the connect string, those would be desirable properties. So the rest of my talk is about an Oracle technology that has these desirable properties to replace these undesirable ones. So just as an example, this is a customer. I'm not going to name them. They don't want to be named, but I'm highly confident that most of you are a customer of this enterprise. They had Oracle database that was sort of in 204 rack. They were running on a X72 with fast local storage. And when they did queries against Oracle, they had a latency. When they put the times 10 cache in, application tier database cache, it was a lot faster. So that was a good thing. By the way, this system was running over 50 million users, and these latencies aren't in milliseconds, they're in microseconds. So what we're saying here is, if you have a system that's incredibly well tuned, like in my opinion, these guys were some of the best DBAs in the world, they were doing queries against rack in microseconds. So the worst one is about 1/4 of a millisecond. So that's pretty good latency. Using the SQL cache, they could go faster. So this was using 50 million concurrent users. So let's just compare that with what that same customer had as a cache. So Oracle was doing stuff on average well under a millisecond. So 1000 microseconds is about a millisecond. The key value stores this customer was using, and they had a bunch of them, on average was taking about 5 milliseconds to access the data. So the cache was taking about 5 milliseconds. Oracle was well under a millisecond. Times 10, you could barely see it. So times 10 was about 12 times faster than rack. And the key value store was about 21 times slower than Oracle. So this customer had clusters with thousands of nodes in their cache, and the cache was significantly slower than the database. So we did this benchmark, and the DBAs said, hold on, why have we got thousands of machines caching when it would be faster just to go to Oracle? It blew their minds, because the developers said the cache was cool, the cache was faster. Until they actually measured it, they didn't know that. Go figure. Here's another example. You've got So this example was using OCI. That's the C programming language for the Oracle database. This one's using Java JDBC. So we're doing operations against Oracle. Oracle's doing pretty well. The worst is about a millisecond. So 1,000 microseconds is about a millisecond. Oracle can go pretty fast even with JDBC, about 100 microseconds to do some queries. The updates, inserts, updates, and deletes were taking about a millisecond. So that's pretty good for an Oracle database. So using exactly the same Java JDBC program, with the same data model, with the same data, running on the same machine, the only difference is we changed the connect string. So going against Oracle was pretty fast. Going against the times 10 cache was a lot faster. How much faster depends. So when I go to some of my customers, they go, we've got huge clusters. We've got the latest and greatest sharded open source technology. We scale. How could you possibly be better? I go, okay, let's look at numbers. For these technologies, the benchmark that everybody compares themselves to is a thing called YCSB, Yahoo Cloud Serving Benchmark. It's a throughput benchmark. You can use as many machines as you want of whatever size. So the largest published numbers that I could see, Cassandra, Cassandra scales really well. You can have linear scalability up to 300 nodes. Sounds cool. It turns out each node goes really slow. So they needed 32 nodes to get about 250,000 operations per second. And I'm saying operations per second because they're not ACID transactions. They're eventual consistency. Eventual consistency is a fancy term for a random number generator. So Mongo could go faster with less nodes for this particular benchmark. As you go down, things go faster. So Aerospike's pretty good. They were doing 1.6 million of these operations with 8 nodes. With times 10, we only needed one node to go faster. So my customers who have these other technologies, I'm showing them, hey, you can get better throughput and lower latency by using less machines. Because these customers are really large and have millions of users, you want to use more than one machine. So this is the same benchmark. As we use more machines, the throughput goes up. So that's 38 million operations per second because the benchmark is operations per second. It's a Java benchmark, you can't change it, you just have to plug in a database driver. Because Oracle times 10 is a SQL database, we just implemented the gets as SQL selects and the puts as updates, inserts, or deletes. So we were using a SQL database with ACID transactions to go significantly faster than NoSQL databases doing non-ACID transactions. Go figure.
Doug, we have a question.
Yep.
What if we lost information in cache data for some reason?
Great question. So I'll answer that. I'm just thinking, I've got a bunch of slides in a demo, so I'm going to speed up a bit.
Okay.
Are you saying we lost the machine, we lost the node? Is that the question?
I'll allow Elise to talk.
Hello,
Okay.
I'm
Hi.
back. Hello. So yeah, this is the idea. Let's suppose any part of the structure that allows caching data is lost. So you cannot storage data in some way to take this reference. So what would be the solution for this problem? Or if there is any, let's say, I'm not saying workaround, but second option to solve this problem?
That is a perfect question, and you're about 3 slides ahead of me, and I've got a demo. So just hold that thought, and I'll cover it.
Okay. Okay. Thank you.
So the point is, thank you for the question. So here's a different benchmark. This is doing 153 million ACID transactions per second. we're doing 20% updates. So we need to deal with redo and undo. So we need to do disk IO. I mean, so this is using 64 machines. So that's about 2.5 racks machines. If we don't do writes, if we just do reads, we can do 1.4 billion SQL selects per second, admittedly with 64 machines. So the point is, it can go, this SQL database can go faster than any NoSQL database. It goes way faster than rack or Exadata. So this product called Oracle times 10, which is owned by the same group that owns Exadata, say this is the fastest database. So just speeding up here. So you can get data into times 10 via anything that Golden Gate can push to it. So just go back to the question. Times 10 is a SQL database. You can use it as a standalone database, or you can use the clustered version. The clustered version, you scale out horizontally, and you have multiple copies for availability. So if one machine blows up and catches on fire, it doesn't matter because you got a complete copy of it. So by having multiple copies of those instances, you have high availability. So read caching with Golden Gate. So committed inserts, updates, and deletes go to Oracle. Doesn't matter which version of Oracle. Golden Gate replicates that to times 10. And I'm going to show you, once the data is in times 10, you're just seeing SQL data in tables, so you can do SQL against that. And I'll show you examples of that. So you can use a single instance or the clustered version. Each of those machines can now be quite large. Because of persistent memory, you can have 6 terabytes of RAM in a 1U machine. Larger machines can have more memory. So you can easily have 768 terabytes with 5U machines. So what used to be impossible even a few years ago, memory is now no longer an issue. So this caching technology uses the same SQL APIs that the Oracle database uses. So whether it's JDBC, ODBC, OCI, .NET, it's exactly the same drivers. If you like the cooler stuff, the Python, the Node, the Go, it all works. There's even obscure things, Rust, Julia, Erlang. If it works against Oracle, it works against times 10 because it's the same APIs. How is it possible? It's not magic. Times 10 is an in-memory database. But we're not crazy. We still persist the data to disk. So if the machine reboots, you pull the power. When you turn it back on again, you go through database recovery and you get back to a transactionally consistent point, just like you would with an Oracle database. You use SQL and PL/SQL APIs, but you do need hardware. You either need 2 spinning disk or preferably an SSD, or if you're rich, NVMe storage. But just because it's an in-memory database doesn't make it magic. You still need to prepare and bind your SQL statements because it has a cost-based optimizer. You still want to have indexes. You don't want to do dumb joins. Like a Cartesian product in an in-memory database is still dumb and slow. Because it has a cost-based optimizer, you still need to update your statistics. So the point is, you can do SQL operations in microseconds. So if you're doing a primary key lookup, that can be less than 2 microseconds on 5-year-old technology. If you're joining 20 tables, it's going to take longer. If your result set's 1 million rows, it's going to take longer. But the point is, you can do things like, left outer joins, nested subselects, cubes, roll-ups. You can do all sorts of fancy things. How does it work? In the prior slides, I showed you Golden Gate can sniff the log and push it, or you can use triggers. With the triggers, you declaratively specify them against the base table. It basically, when the trigger fires, it puts a pointer in a metadata table. and then we poll the metadata table to query the actual rows. So we can do that for reads or for writes. So here's an example of how you do it. We use SQL to declaratively define what you want to cache, be it read or write. So we have a thing called a cache group, which points to a schema and a table and a set of columns of a certain type with some where clause. The side effect of doing that is it creates a schema table with columns with rows. So if you do it with SQL Developer, you click through this stuff. You know, is it read only? Is it read write? Is it synchronous? Is it asynchronous? These are all declarative things. You specify, do you want it to update every 5 minutes, every 10 milliseconds, every 1 millisecond, or continuously? These are all choices. You choose the data types. Eventually, it generates SQL. Here's a more complex example. Like this example is a single table. This is a hierarchy, parent-child. You can have hierarchies as deep as you want. This is going to update every 1 millisecond. So you know how stale the data is because you choose what that interval is. For things that need to be up to date, you have a small refresh interval. For something that only changes once per day, you don't need that sort of thing. So how do you do this stuff? If you know how to do stuff with an Oracle database, you're overqualified because it's just another SQL database. We use as much as possible the same APIs, same data types. So looking at the time, I think I'm going to jump to a demo.
We have one more question.
Yep.
You've showed the user managed option for creating cache. What is the difference from the other ones?
That's a great question, which is a long question. I'll do the demo and then I'll come back to that question. I just want to get the demo on.
I'll leave it open.
Okay, so this demo is using Kubernetes because all of my customers have gone away from VMs and they're all running in containers. So this happens to be running in Oracle Cloud, but it runs exactly the same in AWS or Azure or Google Cloud, OpenShift, whatever your favorite technology is. So I'm essentially SSHing into my container. I could get my mouse back. So I had, created some users, done some grants, created some tables, ran some PL SQL to load some data. I created some more tables. And these tables, they got primary keys, foreign keys. Because I'm using the clustered version, I'm saying how the data is distributed around. Is it by reference? Is it by hash? Is it by duplicate? That's all a whole talk in itself. So I'll just ignore that. So I connect, I go to my cheat sheet. So I'm just describing tables, the data types, nothing very exciting. It should look very familiar with Oracle. Just run some simple queries. Hold on. Run the queries again. So this primary key lookup, that was taking 32 microseconds. But I'm doing this from a prompt. So this is dynamic SQL. If I ran this in JDBC or ODBC or OCI or .NET or whatever, it would be a lot faster because I would have prepared the SQL statement. I would have bound the bind parameters. So it would go a lot faster. So this is a clustered database. So I'm doing a join across 3 tables and it took 83 microseconds. So with most clustered databases or sharded databases, number one, you probably can't do SQL, or if you can do SQL, you can't do joins. So the point being, this sort of SQL with left outer joins and nested subselects, the same SQL works even though it's on a sharded database. So with something like with Oracle sharding, great product, you need to pass in a shard key. With this, you don't need it to pass in a shard key. So I'll just go back to the talk. So just in so I want to summarize and then we'll do questions. So in summary, caching is useful if you have lower latency. As a bonus, you get higher throughput. If you can use the same data types and the same SQL for your caching application as your system of record, that means you don't have to rewrite your application. You can just change your connect string. So if you've got lower latency, higher throughput, and don't need to rewrite, and you're using the same SQL APIs as the Oracle database, that means the cost of converting your system to use a cache is low with respect to development effort. If it has significantly lower latency and higher throughput, that's a bonus. You can use other technologies, but if the throughput is worse, if the latency is higher, and if you have to rewrite, what's the point? So using this caching technology, you can either do it via log sniffing through Golden Gate for Oracle and a bunch of other databases. If you're doing with times 10 against an Oracle database, you also have the choice of using triggers on base tables. So that's what I wanted to cover. Now, there were some questions that I deferred. Could you please remind me what those were, Patrick?
The question is, you've showed the user managed option for creating cache. What is the difference from the other ones?
Right. Okay, so there's about 10 different types of what we call cache groups.
Hello.
Yep, hi.
Yeah. So basically, we had 3 options in the list when you take the list there, and you said about the right ones, read only, and then we had the user manage. So when you're creating a cache for caching data, what's the difference from the other options? Because I couldn't visualize it completely. Can you go back in some slides, please?
Yep.
If possible.
Do you remember which slide it was?
Before. Yeah. In these options, you can decide for a type. Yeah, user managed.
Yeah. Okay.
This
so
one. Okay.
When you're caching, you're mapping tables in your system of record to tables in your cache.
Yeah.
Some table, and they don't all need to be the same. Some reference tables will tend to be read-only, and you may not update them all that often. So you can make that a read-only cache. A logging table, you might want to write to a lot so fast that your Oracle or RAC or Exadata can't keep up. So maybe you would make that table a write cache table. So what I'm saying is, based on the usage of the tables in the data model, some tables may be read-only, some may be rewrite.
Okay. So you can customize it.
Absolutely. So you make these decisions on a table-by-table basis. So things like read-only is for reading. When we say write through, that's for write caching. Do you want to write to the Oracle database asynchronously, which is fast, or synchronously, which is slow, because you've got to go over SQLnet and you have to wait for the commit. So these are behaviors. They're predefined behaviors. User managed is, so you, via hints, basically tell us what behavior you want. So these things have a whole lot of properties or constraints or way things work. We've predefined because we believe they're the most common use cases. With user managed, you've basically got a framework and you can pick and choose the behaviors. Is it synchronous? Is it asynchronous? How does it update? How does it refresh? You get to choose. So 20 years ago, we started out with a framework and we say, as a customer, you choose the behaviors you want. over about 20 years, we said, hey, there's very common patterns. So we predefined those patterns. And about 95% of people use these predefined patterns. So I'm showing 4 options there. Nowadays, there's over 10 options, like PayPal just got us to add another option based on the sort of stuff they wanted. Great question, thank you.
Thank you also.
Any other questions, Patrick?
Not at this moment. Maybe people do still have questions.
So if I just summarize, I'm not talking about ResultSet caching. We take data, say it's read-only caching, and we stick it in tables. When the data is in those tables, you can then run queries against those tables, the cache tables, with different join conditions than what was originally queried. But because they're tables, you can join against 1 or 10 or all of the tables, even though the original thing that populated the cache may have been a table at a time or a hierarchy. With ResultSet caching that I showed in earlier slides, you can't do that. With this, you did some query to populate that result cache. This stuff, you can't let's then rejoin it. It's already done. It's hard-coded. When you cache whatever to the model there, I can query just that table or master detail or master detail detail. I can do whatever query I want because those tables are just tables and I've got the power of SQL. So we cache the data from tables to tables, and then you can do your own queries against those. So it's much more powerful. Because it's running against a memory database, it's really fast, it has high throughput, and because it's still using SQL in the same data types, you tend not to have to do complete rewrites where you would over here. That's kind of the summary of the talk. Read caching tends to be far easier because you know what the system record is. When you're doing write caching, it gets far more complicated because you need to figure out which is a system of record. You either allow it, but you have to constrain the system, or you flat out disallow it. Any other questions, Patrick?
Well, I have a question myself. Oracle also gives us the in-memory option for the Oracle database. How does that relate to the times 10
Great question.
product?
So Oracle in memory is a feature of the Oracle database. So it actually runs on the same box, it uses the same SGA, and it tends to use a columnar representation of the data to do faster analytics.
Yes.
So Oracle in memory is all about doing, faster queries, faster analytics. Times 10 is a row store that does faster transactions. So if you want to do faster ACID transactions, use times 10 in memory database. If you want to do faster analytics, use Oracle in memory. So both of those products are owned by the same VP. Both of them have Oracle in memory in the name. Kind of confusing, but they're for 2 completely different use cases. Oracle in memory is awesome for faster analytics. You can scan billions of rows per second. Times 10 is for faster transactions. You can do billions of queries per second, individual select statements. Returning 1 row with Oracle in memory, you might do 1 query which scans billions of rows. Did that explain the difference?
Yes.
Thank you, Patrick.
Okay, I've got another question. What if something is not cached? Will the system try to get it from Oracle database automatically?
Great question. The answer is yes, you can. So we have something called pass-through. So we just set, there's a couple of ways of doing it. You can use a SQL hint, or you can set an attribute. So if you want to access some table that's not cached, you can just turn on a SQL hint and it will use SQLnet, query Oracle and give you the answer back. Something we just did for PayPal. If the result set is less than some number of rows, query Oracle and populate the cache. If it's more than a certain number of rows, query Oracle, but don't update the cache. So their rationale was, if you have data with a small result set, they want to cache that because they want to reuse it. So say it returned 100 rows, they want to cache that because it's a good use of memory. If the query returned 10,000 rows, they probably don't want to cache that because it's going to take up a lot of memory, which could be used more efficiently elsewhere. So we just added a SQL hint that gave you the threshold over which how many rows you cache or don't cache. So I've just talked about the simple stuff. Like I said, there's 10 different types. There's things like pass through. I just explained a condition where you conditionally cache or don't cache. There's lots of different options. I'm just doing the high level stuff. There's lots of cool details, but that's a whole nother talk. Any other questions, Patrick?
No, I don't think so. Nothing anymore.
So thank you, Val. Over to you, Yeli.
Yes, thank you, Douglas. Thank you for a great talk. Even for me, it was quite good to understand. So thank you for that. Also, everyone who posted questions, thanks for the interactive part of this. Okay, for now, I want to wish everybody a very nice afternoon. Enjoy the good weather. And next week, we will have Toon Koppelaars. So again, Douglas, thank you. And well, we hope to see you sometimes in the Netherlands again. Bye-bye.
Okay. Doei.
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 Doei, doei.